Hello, and welcome to Lecture 21 of AMAT502 at UAlbany. Today, we're going to continue our review of probability and how it influences machine learning methods. Last lecture, we discussed naive Bayes classifier. Today, we're going to talk about Bayesian regression, specifically underneath the form of logistic regression. So I just want to continue to remind you of all the wonderful textbooks that are out there, which you should consider picking up a copy of if you're really serious about pursuing data science as a career. One of the ones that I sort of discovered recently, at least in the past year or so, is this second edition of Joel Gruse's Data Science from Scratch. This is a really good book, which asks that you basically learn to code up a lot of these machine learning methods from first principles. And so instead of using scikit-learn, you're going to use your own know-how of Python to develop this. My only critique of it is that it tends to use a little more type-based programming. So you have to be really clear about identifying the types of inputs and outputs. But there's good philosophical reasons for wanting to do that, at least from a computer science point of view. Additionally, and much larger and more on the math side, less programming focused, is Bishop's Pattern Recognition and Machine Learning. This is a canonical text. It's really wonderfully typeset, and it really does a good job of highlighting sort of the Bayesian perspective. It has little bios on people like Laplace and what have you. Either way, very good, a little bit on the heftier side, but definitely a good book with exercises, and of course, things like Bayes' theorem. All right, so I did like a joke that I learned from Gruse's book, which was what makes a data scientist different from a statistician and computer scientist? Well, a data scientist is someone who knows more computer science than a statistician and knows more statistics than a computer scientist, but knows less about each of those other people in their respective fields. So this kind of goes to the whole point of data scientists being sort of a jack of all trades and not necessarily a master of any single one. All right, so the topics for today, we're going to do a quick recap of basic probability, conditional probability, Bayes' theorem, and introduce the principle of maximum likelihood. This will allow us to revisit linear regression and sort of appreciate the sum of square residuals as a really meaningful penalty function. And then all of this sets us up for another case study and how to apply the data science pipeline with the new method in tow, which is logistic regression. And the probability will help explain how logistic regression works under the hood. All right, so a quick recap. In probability theory, at least traditionally as defined by Kolmogorov, we have some sample space that contains all possible outcomes of an experiment. You can think of this, the outcomes of flipping a coin or rolling a die or what have you. Probability sort of first starts off by talking about, well, what events can we discuss? Events are subsets of this sample space omega. In the case where omega is finite, all subsets are fair game. But when we start looking at processes which have outcomes defined inside of Rn or have some sort of uncountable set of possibilities, we need to be a little more careful about what it means to be an event. It's the whole purpose of all the measure theory that we discussed last time. But either way, sticking with the simplest scenario, imagine we roll a die, and the die has 6 possibilities, 1 through 6. And we could let A be the event that when we roll this dice, 1 comes up. And another event could be that the outcome is odd. So there, the event was a union of possible outcomes, 1, 3, and 5. So conditional probability is defined by saying, well, let's say I know that some event B occurred. So for example, we know that the outcome was odd, or someone told you. How would you update your degree of belief that the outcome was actually 1? So if I roll a 1, 3, or 5, obviously a third of those possibilities are going to be 1. So that is reflected in this conditional probability of rolling 1, given that the outcome was odd, we now update to be a third. Whereas normally the probability of A alone would have been a sixth because there are 6 possibilities. Bayes' rule also allows us to update or to switch around the order of conditionals. And in particular, one thing we can do here is look at what's the probability of B given A, and it's not equal to just the probability of A given B. Instead, we need to multiply by this ratio of probabilities, probability of B divided by probability of A. So in this example, the conditional probability of rolling an odd outcome, given that we rolled a 1, has to be 100%. So that's also evidence to you that probability of A given B is not equal to the probability of B given A. All right, so I alluded to in our last lecture that there sort of Bayesian philosophy is one where we really change the significance or meaning of these events A and B. We don't think in terms of just subsets of an outcome space, but rather we take sort of a much more abstract point of view. So we're going to relabel some of the ingredients inside of our formula for Bayes' rule and use instead things like hypothesis and data. So in Bayesian inference, we sort of set aside the idea that conditional probability is just reserved for talking about subsets of an event space. But rather, we're going to say, let A be the probability that some hypothesis is true. And then we're going to say, given B, where B is some data. So notice this is already very different than what we just set up with omega and subsets of omega. But somehow it makes more intuitive sense. So hopefully you can roll with this. General language here is that we think of P of H as the prior. This is the probability that the hypothesis is true. But really, you want to think of it as a probability distribution. So it's not so much the case that what's the probability that this hypothesis is exactly true, but rather, especially since our hypotheses tend to lie in some continuous space of parameters, like, oh, what's the mean and variance of some distribution? We're now asking, oh, what's the probability that our parameters that govern these models lie in some range? You can think of that as P of H. Now, of course, if we just have sort of a null model, like when we're talking about hypothesis testing, we want to see how we can update or see if data influences our choice of model and causes us to want to change the parameter values. So we gave this example of, suppose you have a coin, you want to flip it. How do you know that it's a fair coin? You might start with the hypothesis that this is a fair coin, but then given some data, how do you update your hypothesis? And so this is all encoded via this sort of conditional probability looking formula. So the probability of H given D, think of that as the posterior. This is the posterior distribution on our parameters that govern the model. So in the case of flipping a coin, this is how we change our value P in the Bernoulli distribution. Now again, in Bayes' rule, the whole point is we want to be able to flip around the conditional. And so then we get this somewhat weird statement. What's the probability of our data given our hypothesis? So that's another way of thinking about how hypothesis testing works. Is, if we assume that we have a fair coin and then we look at flipping it a couple times, we can ask, well, underneath our null model, how likely is that data to be? And that's why we call this probability of data given H, the likelihood of the data given the hypothesis H. This is sort of what we think of as giving evidence for H, or maybe it's going to give you evidence for something that's different than H. But anyways, finally, just to complete out the sort of analogy, we can think of P of D as the probability of the data. aggregated over all possible hypotheses. So, I want you to take a moment to kind of reflect and think about this. If you've only ever seen probability in the sense of, here's this outcome space omega, subsets of this outcome space define events, and then via Kolmogorov's 3 axioms, we have probability as being a thing which assigns non-negative values, or something between 0 and 1, to every subset or nice subsets of omega. And then just try to think, how can you tell that same story here underneath this Bayesian framework? Feels a lot more different than what we were used to discussing with rolling die and so on. And you might ask yourself, are these even mathematically well defined? But either way, let's go ahead and go through and say that, well, one reasonable answer is that, this is these things aren't mathematically well defined. And in fact, this is one of the main arguments which goes in this whole Bayesian versus frequentism debate. So this book, Bishop, that I held up earlier, is very much written in the Bayesian school of thought, and it's definitely become the sort of favored winner here. So in some sense, these are arguments from the past. Anyhow, first, when we're trying to spell out what the probability measure is on this sort of space of hypotheses, it doesn't really make sense. But actually, it does if you first think of, like in our coin flipping example, maybe all possible values for p, the probability of getting a heads, is equally likely. So that's as we have our uniform distribution. So then that actually kind of makes sense. Anyhow, so in practice, this amounts to simply putting a PDF on the space of parameters. So that's really how we sort of can save Bayesian and say that it is really mathematically well defined. But again, the sort of the frequentists would say, well, how do we even know what model we need to use in order to put a probability distribution on the space of hypotheses, or parameters, I should say. So frequentism just purely lives in the land of, I'm going to repeat an experiment a bunch of times and count the number of times an outcome is observed. So this is sometimes why frequentism is called non-parametric. So you don't need to posit a model. You don't need to consider the parameters of those models. But again, Bayesian sort of had its favor back in the 1800s, but then in the 1900s, frequentism was really dominant. But now we're actually swinging back to Bayesian probability and inference. And part of this has to deal with the fact that we can actually take this philosophy of putting PDFs on the parameter space and then using computers to sort of update and change our parameters using something like gradient descent, or even nowadays we have stochastic versions of gradient descent, which is a much more efficient computationally. That basically just sort of randomly climbs down some gradient flow where we're trying to maximize and minimize some function. All right, anyway, there's lots to read here. I think these MIT notes link to the same notes from last lecture. All right, so all this may sound very abstract, but let's go ahead and look at a very particular example. So suppose I'm given a coin and I flip that coin 100 times and I get 55 heads. We might ask, how do we model this? Well, again, what we do is we assume that the probability of heads on any given flip is p. And so we're thinking of these 100 flips as being part of some IID process, independent, identically distributed. And then that number of heads comes from just counting up the number of successes in the sequence of Bernoulli trials. Now, the thing which counts the number of successes in a sequence of Bernoulli trials is called the binomial distribution. And so we have the binomial probability mass function, which basically says that assuming that the probability of the heads is p, we don't know what p is, probability of getting 55 heads, assuming p corresponds to the probability of getting heads, is, well, first we need to take the fact that we flipped a coin and got heads 55 times. So by independence, that means the probability of 55 heads in a row, for example, would be p to the 55th. And then let's say the remaining 45 flips are all tails. And what's the probability of that? Well, again, by independence and law of complements, it's 1 minus p raised to the 45. But we can mix up where those heads and tails happened and the number of arrangements that we can distinguish or maybe there's a few heads and then a few tails and so on and so forth. The number of ordered sequences of heads and tails, we're at 55 heads and 45 tails. It's counted by this binomial expression right here. It's 100 choose 55. You're choosing the 55 locations where the heads is, where the heads are. So one of the methods in sort of Bayesian inference is that we want to sort of rewrite this very traditional formula from basic probability theory, something you'd see in AMAT502 here at UAlbany, for example. And you want to think of this now as a likelihood function. So now we're going to ask, all right, let's show that this probability calculation really depended on P. P is our parameter for this Bernoulli process. And so the likelihood of P is just given by, as a function of P, whatever this number is. So really you could think of this as likelihood of P given the data. So maximum likelihood estimation basically says we should choose our parameters in such a way that makes the observed data maximally likely. That makes good sense. Now let's see how we would do that. Well, again, we want to maximize a function. We just use calculus. Calculus is built for allowing us to maximize and minimize functions. So what do? We take this expression here and we differentiate with respect to P. We set it to equal to 0. That's how we find critical points of a function. And so by using some combination of the chain rule and the product rule, we then get that this derivative, well, you can take the product of the first times the second, and then plus the derivative of the second times the first. That's where this minus sign comes out from. And again, these are polynomial expressions, so we just lower the exponent. So that's why we have a 55 here. P to the 54, that's the derivative of the first times the second. And then I have plus derivative of the second, but the second, the chain rule, of course, brings the 45 down, and I have 44, but then differentiating what's inside gives me that minus sign, and that pops off and appears here. Times P to the 55. That's the first expression. Set this to 0, rearrange terms, get rid of what's not relevant. We end up deriving this equation, which is that our critical point of the likelihood function lies at what we call P hat. P hat is 55 over 100. So basically, our empirical or sample mean ends up being our maximum likelihood estimator for this likelihood function. All right, so let's go through that in a slightly different way. So because so many things in probability and statistics are modeled by a bunch of occurrence of independent events, but where each event is governed by an identical distribution. That's what we mean by IID. It's often very useful to help split up all these products and exponents using the properties of log. And so this is why we sometimes talk about log likelihood. So what happens here is, and this is one of the really beautiful aspects of the function log, is that it basically, turns our products into additions and our exponents into multiplication. And it also doesn't change where critical points are. So in particular, if I ask, well, what's the derivative with respect to x? Before I was saying p, but now let's just go back to normal calculus. Just think of this as a function L of x. So if I take the derivative with respect to x, set that equal to 0. Well, again, the chain rule says that, all right, well, the derivative of log is 1 over whatever's inside. And then the chain rule says I need to take the derivative of the next thing. That's dl dx. But, assuming this L of x function is nowhere 0 on our domain, first of all, that means that this expression exists. But then additionally, it's not going to affect where the derivative is 0. so it means that we can use derivatives and critical points of the log likelihood function to find critical points of the likelihood function. So just running through the calculation we just did with the flipping a coin and getting 55 heads. Now if I deal log likelihood and looking at log of this binomial expression, which again separates out because log of A times B is log of A plus log B, ends up giving us 55 log P plus 45 times log 1 minus B. So here I'm already using the fact that exponents come down when you take the log. And then I separate off this constant expression as just as a sum of a constant term. That's especially appealing because when we take the derivative of a constant term, we always know that's 0. And so then derivative of this expression ends up looking a lot simpler. So we have 55 over P minus 45 over 1 minus P. And again, just verifying that when we set that equal to 0, we get that P hat, the location of our critical point for the log likelihood function is the same as the critical point of the likelihood function. So I encourage you to go look at some more of these notes. And so these were some earlier notes from the MIT probability where I took this example. And so if you want more derivation, you can look there. Also some really nice notes that come out of the ecology department at UMass Amherst, and sort of going at how do we use these sort of frequentist versus Bayesian perspectives and log likelihood there. So that's just links to further reading to enhance your statistics education. All right, so let's go ahead and try to apply some of these concepts, not to coin flips, but to a situation which seems much more familiar. So we think of normal linear models when we're doing linear regression as being trying to predict my dependent variable y using some linear combination of my independent variables x. But this time, let's go ahead and take into account that data is fundamentally noisy. So I'm going to have some epsilon I as well. So this would be our model for how do we linearly predict outcomes on the presence of noise or error. So again, the most classic assumption is that this error term is governed using some Gaussian distribution. So then you might ask, well, I want to know what's the probability that my predictions are going to lie in a certain range. Well, you can always end up integrating or finding area under the curve of some Gaussian function. But anyhow, we can think of this expression here where now we showed the dependence of our model on beta 0 and beta 1 as, well, what's the probability of observing xi comma yi given this hypothesized dependence of our model, beta 0, beta 1? Well, we just take the fact that we've got this error term, beta 0 minus beta I xi, that should be beta 1, my apologies, beta 1 xi, that is the predicted value underneath that linear model. So you can think of that as of course, the prediction. And now you want to ask, well, knowing that I have noise in my model, how far is this going to be off from the true label? Well, there's my true label. And then I know that even if I were to be able to predict perfectly with the presence of noise, I know that this difference, or the difference between whatever my actual value is from my predicted value, is governed by a normal distribution. That's exactly what this says. So you want to think of this as sort of the mean of your distribution. So that's where we hope the truth lies, but then we also understand that the data is noisy and that we might shoot above or below, but that difference is governed by a Gaussian distribution, which of course requires the choice of some sort of variance or standard deviation parameter. So now let's imagine we do this a bunch of times. And so now we're again getting into the definition of likelihood, which is sort of the probability of our observed data, given these hypotheses of how we think our data is fit using a line. that line being governed using the coefficients beta 0 and beta 1. That's our constant term, and then our linear term, beta 1. Well, again, we assume that each draw, or that each instance of noise, if it's really truly noise, is going to be independent of one another. So that means that the likelihood or the probability of our data, assuming our parameters are correct, is going to be given by this product. Because again, each observation is independent. So if I want to find the probability of all n observations, that means I have n samples, n points that I'm trying to fit, then it's going to accrue error in the way of that's given by this this product, or at least that's the probability is going to be governed by this product. So that's a very complicated expression. I would not want to differentiate it, by hand. But again, luckily we can use logs. And so if we consider not just the log likelihood, but let's go ahead and use this minus log likelihood, just accounting for the fact that this Gaussian parameter comes with e to the minus something that looks like x squared. That minus is going to come down when we apply the log function. So just to make things simpler, we use the negative log likelihood function. And then somewhat miraculously, or not so miraculously, this product of these Gaussians turns into the sum of squared residuals formula, plus to some constants. So this is, I think, really remarkable. Before, when I had first introduced the train model predict paradigm as sort of outlined by Guttag, and I looked at, well, it's the simplest example of how we might predict from observations. We use number sequences. We use the Fibonacci. We use these other sort of linear sequences, geometric. And then we just said, well, let's assume a linear model. And so part of our modeling step while our predictions were off is we kept updating and tuning your parameters so that we could minimize some penalty function. And I said, you know what, let's pick a penalty function that takes our prediction, looks at the true value, squares that difference, and then adds it up across all the observations. I even asked, why would we do such a thing? Well, there are reasons which go back to just the fact that these methods were developed by Gauss and people before computers existed. And so because the calculus was sort of hot off the press, it was easier to differentiate an expression that looked like something squared, rather than say like the absolute value, where the derivative doesn't even exist at the origin. But now we have a completely different justification. We've come to expect that error might be normally distributed, and that itself might be a consequence of the central limit theorem. But here, once we take into this normal assumption and our error, using a linear model, it actually looks like the best way to sort of evaluate the quality of our model from a Bayesian perspective, when you take this negative log likelihood function, is the sum of square residuals. I think that's really remarkable. And then moreover, finding what pair of values, beta 0 and beta 1, minimizes the log likelihood function is exactly going to be the same formula that we tried to minimize when we were just doing this by hand with sum of square residuals functional. And so just doing calculus actually turns out to be, well, calculus after doing some Bayesian modeling and some tricks to simplify the math. And so that's kind of a really nice dovetailing of these two different stories, which all just shows that this was a really good penalty function. All right, so there we sort of did a recap, some basic probability. We talked about also how can we think of linear regression in terms of this likelihood paradigm, which comes to us from Bayesian inference. Let's go ahead and try something different, because not everything we're going to look at is something that's governed just using a linear model. And so let's look at something that's going to be very important, especially with election day just around the corner, meaning Tuesday. And please, regardless of your political preference, please vote. Anyhow, let's look at this sort of sociological study. Suppose we want to predict whether someone is going to vote for Trump or not. And so one way we can model this is by saying, all right, I'm going to look at certain features of the people who are voting. I might want to look at, say, their age and their income. And so if we try to just use a linear model, first of all, this doesn't really make sense because we're trying to treat a categorical variable, which is yes or no is a Trump voter, into something that's sort of scalar or numerically predicted, because both age and income are scalar quantities that could vary continuously. They're not categorical quantities. Anyhow, so if we try to just write up a linear model like this for predicting whether or not someone's a Trump voter, it's not really going to make sense. But it turns out there's a trick that we can use. And this is given by what's called the logistic or sigmoid function. Essentially what this does is it transforms the real line of possibilities that you get from using a linear predictor into something that sits between the interval of essentially 0 and 1. And we can kind of think about how that works here, because if we think of x as the output of this dot product of this linear prediction, well, for a really, really large x, e to the minus x is going to be 0, which means this expression tends to 1. And for really, really negative x, s is going to turn out to be really, really big. E to negative of a really large negative number, it's going to be something really positive. E to the something really positive will be very large. It's going to dominate this. Something like 1 over a billion basically tends to 0. So now we basically squish the whole real line to sit between 0 and 1. So let's go ahead and sort of treat this. But one thing to appreciate is that in the case where we're uncertain, we get a dot product, which is the way we can think of this linear prediction being close to 0. This might mean that our features that we're trying to use to predict whether or not someone's a Trump voter is orthogonal to the directions that really matter. So in that case where things are sort of orthogonal, you can't predict very well. Our dot product is going to be 0. If we think of x as the dot product, e to the 0 is 1. We have 1 divided by 2, it's a half. Which is perfect interpretation. It's a 50-50 shot of whether or not someone's a Trump voter or not when we're looking at irrelevant features. All right, so let's just go ahead and get a sense for what this looks like. So of course, just being my first time through, I gotta hit Shift Enter twice there. I did all the usual things. I just defined the logistic of x to be exactly that expression. Of course, I use x, the e to the minus x function. I had to import my math library, so import math. And then I just use list comprehension to produce a bunch of logistic of x values. That's just basically f of x. And then I plotted that here. And you can see that does exactly what it looks like. For large negative values, minus 10, it's close to 0. For large positive values, positive 10, it's close to 1. So we're now going to think of, instead of using linear regression, which we think of as just sort of taking dot products of features against some set of parameters, we think of the parameters sort of governing how much does this feature affect or depend on or predict our outcome. Again, that dot product is going to be some real value, but we want a number between 0 and 1. So we pass it through this filter function. That's our f. It's our logistic function, our sigmoid. That's 1 over 1 plus e to the minus x. Of course, I'm just sort of using is e to the minus whatever the dot product is, which is beta dot x. And so let's try to run through some of the analysis we just did, but now take sort of a probabilistic approach. So if we think our parameters beta, this is the thing which encodes dependence of whether or not we think someone's a Trump voter. That's the thing we're trying to predict. It's our target value yi, given our sample xi. Xi is a vector of things like age and income. So given our parameter beta, our model says that the target value yi, for example, should be 1 with probability f of x dot beta. Again, probability, now that f of x beta lives between 0 and 1, we can think of it as a probability. And so So we can think of, again, the way we set this thing up, we're trying to predict, yes, this is a Trump voter. So yes, the dot product's large. So we'll think target value, yes, a Trump voter, we encode that as 1 with probability this number. And then no, not a Trump voter, 0 with probability, well, 1 minus that just by law of complements. So now if we take a bunch of observations, so meaning we take a bunch of people, we measure things like their age and their income, and then we just ask, you know, did they vote for Trump or not? And then we just treat each of those F of that, you know, sample dot our parameter values beta, pass it through, again, I said F. Then I can use the fact that yi is 1 when it's a yes to think of this likelihood function as being the probability that our prediction was true. So notice F of x dot beta, when yi is 1, that gives us our probability. So that was like a yes coin flip. And then whenever yi was not 1, so meaning 0, that showed that the person was not a Trump voter. And again, we're thinking of that probability as being 1 minus whatever this number is. That's our P. And so we just basically take this product over our samples. And notice we don't need to have this sort of binomial coefficient because we can think of the data as being ordered in this way. And it turns out not to matter for the purposes of likelihood, or I should say the derivatives of this likelihood function. So anyhow, so now we have this really complicated looking expression where we've got likelihood is basically this product of all the yes outcomes, which each had probability P. P is F of xi beta, and all these no outcomes, which was like 1 minus P raised to the how many that was. And so anyhow, when we take log of that expression, again, this is for a single observed value. So actually, I'm sorry, that wasn't a long product. It's just, you know, that number raised to the yi, or 1 minus F of that number raised to the 1 minus yi. Then if we take log of this, again, exponents come down. So yi is now down here. Products turn into sums. That's why we now have a sum. And then again, that's the exponent that was sitting over this. And so, you know, if we're trying to take this principle of we're to choose our parameters in such a way that makes our data maximally likely, then what we need to do is find this set of parameters, beta hat, that maximizes this log likelihood function, which we can find via differentiation. Now, of course, part of the problem here is we have this dependence on a whole vector of values. Xi, again, that's our sample, but the features are in some d-dimensional feature space. So J ranges from 1 to D. And so with regards to every one of those coordinates, this feels like a single variable calculus problem. So looking at the partial derivative of log of L beta in the jth direction ends up giving us an expression that looks like this. And you know, I leave it to you to sort of check this because it's a somewhat painful calculation. But anyhow, if you look hard at this and you realize that, well, due to the nice properties of the sigmoid function, if I'm just interested in where this is 0 or how this points, you know, I can disregard this derivative f prime because it ends up being just sort of a positive scalar. And then this part here also ends up being, I believe, always positive. Yeah, if we stare at that. And so then the thing that really drives this gradient is this yi minus f of xi dot beta. So f is again evaluated on the dot product times whatever that function value was in our coordinate. So again, you always are evaluating this gradient at a point. So the whole point of all this differentiation is this is going to actually give us a sort of vector field on our parameter space, which allows us to then sort of flow to, without actually analytically solving for what are the critical points of the log likelihood function. We can instead just figure out locally what the derivative is of the log likelihood function, set up a vector field, and then just follow gradient descent to then be attracted to whatever the minimum value is, or the maximum value. All right, so that's all the theory. And now let's go ahead and use the tools as given to us by Python and scikit-learn. We're going to look at a data set, which I believe I got from this Geeks for Geeks website, which illustrates a nice case study of machine learning and also shows some of these pre-processing steps that you might want to take in your final projects. So anyhow, just a review, the data science pipeline, I think of as having sort of 6 steps, 5 worth numbering. First, of course, is to collect or load data. We almost take that for granted, but it's actually a non-trivial start. How do you choose your data sets? Well, you need to choose data sets that are available to you. But then once you've got the data, you can really start the pipeline. So you want to do sometimes called EDA. It's the exploratory data analysis step. And often visualization is very useful here. Sometimes you really just want to like read off some of the attributes so you understand what you're working with. Once you've got a picture of what's going on, you can then consider what machine learning methods you want to use. So that's again sort of in the conceptual brainstorming step. And now you get down to actually running the code. So you create instances of your data science method. Again, you think of each of these as being classes, and you're creating instances of these classes in an object-oriented programming sense. And then you update attributes of your objects via some of these train and predict methods. All of this allows you to then produce predicted values and then analyze the results. And so maybe you're not satisfied, but you shouldn't just give up. You need to consider what more you could have done. Maybe there's some pre-processing. Maybe if there was missing data, you could replace the missing data with averages for that feature, so on and so forth. Again, you need to really show a good-hearted attempt at improving your classification results. All right, so let's see how that works in this case. All right, so here we're going to be looking at it's called the employee data set. I don't know really what it's from, but we'll just look at it, and I have it provided to you as a comma separated value sheet CSV file. So, brought in pandas and NumPy, and of course matplotlib.pyplot in order to plot things. And so we want to kind of check out the data. So let's just, all right, great. So what have we learned here? So first thing your eye should get drawn to is, all right, 400 rows, 5 columns. So that means we have 400 samples, 5 features. But maybe not all of them are features. That's why we need to look at the actual data set. And so we can see that there are some things which maybe aren't really useful. So like right now we have just the order in which our data frame this exists. That's indicated by this first column. But then we have a user ID, which is essentially just it's just a name. You don't really want to think that a name is going to directly predict, or you might be hard coding that feature too much. So this column is sort of useless. And then it looks like just based on this last column, we have this purchased. You now have the sense that like, the goal of this data set is to use some of these attributes like gender and age and salary to then predict whether or not that person purchased a product or upgrade or subscription or something. So you actually want to think of this as your target. This is your Y column. And so then really we now only have 3 interesting features: gender, age, and salary. And then from those 3 features across our 400 samples, we're trying to predict 0 or 1, purchased or not. So this means we're in a classic classification setup. And so that leads us to this question. And so we're going to ask, and again, this is really important. Data scientist has the name science in it. So you want to be formulating hypotheses and then testing those hypotheses. So here's a hypothesis. Age and salary predict whether or not someone bought a product or not. All right, and so of course we formulate that into a question. And then we see what happens once we've identified this hypothesis. So this is a really important step in your projects. You need to always think about, what question am I asking and trying to answer using my data science methods. So in this particular case, we disregarded gender because we want to work with something that's clearly numerical in order to apply this sort of dot product and then use logistic regression. So we're going to extract out those features. And let's just go ahead and make sure I did what we wanted to. Yeah, good. So it looks like we've got clearly an age column here and our corresponding salary column. And so some people only making there's 19, making 19,000 a year. And then there's some 32-year-old making 150 grand, and so on and so forth. So again, just visually inspecting and thinking about the data. Again, you have one of the best machine learning devices is in your head. So think about what you're doing. And so let's now also take advantage of our eyes as a sort of data science tool. And so we can plot our data and then color code our scatter plot according to yes or no, did they purchase the product or not? So 0 or 1, 1 being yes and 0 being no. And so we're now revisiting our question. Do we think that age and salary determine whether or not someone purchased this product or not? Well, here we actually see a very, very clean separation or at least clustering in some sense, where everyone who made less than 100 grand a year and was younger than 40, I think did or did not purchase the product. I forget which one is yellow and which one's purple. And then but then we ask ourselves all right, well, what we see here now is sort of almost an or condition. So either you were older than 40, in which case, regardless of salary, you, we'll say, bought the product, or you made more than 100,000 and it didn't matter how old you were. So you could be younger than 40 and also buy the product. And so this kind of clean separation suggests that you're really onto something. So let's now try to use some data science methods to help establish or prove your hypothesis. All right, and so this now gets us into a sort of train model predict paradigm now as embodied using the scikit-learn API. So we've chosen a method, we've chosen a question, and because we've been talking about logistic regression, that's going to be the method we're going to use. So as always, we need to separate our data into training and testing portions. This allows us to actually test our hypotheses. On our training data, we're going to apply the .fit method. And then once you've carved out candidate X values, which correspond to the X test portion, you're going to run predict on that part of the data on X test. This is going to produce for you a value, predicted value. Yes or no, did they buy the product? And then you get to look at your reserved data, your testing data, and then compare. Was I right or was I wrong? Again, one of the beauties of supervised learning tasks is that we can have a quick yes or no answer to sum up and find out our accuracy. And that's our last step. So we need to evaluate our model's accuracy. And here, a confusion matrix is really useful. So let's see these steps in turn. All right, so got our data, and we're using the train test split function, which is going to produce for us a sort of tuple of rows and columns. All right, so that should all be in there now. Now we're going to apply fit on X train. So again, classifier, again, this could have been any name that we wanted. It could be Bob. Bob is going to be our object of the logistic regression class, where we've equipping it with this random state 42, because we understand there's going to be some random seeding. And again, you should look up scikit-learn for whatever particular method you're applying, see what parameters do you need to provide. But either way, we now fit it on our X train and Y train. And so we have a pink box here, which just tells you that we should be warned. Some of this is going to be deprecated soon, but in general, we're going to need to specify what's called a solver to silence this warning. But that's a future warning, the problem for future Justin. All right, so now once we've trained our data on our classifier object, let's now apply predict. And again, we separated our data into a train test split, but each of those train and test splits had an X test and a Y test, an X train and a Y train. And so now we're using the X test. So let's go ahead and run it. Okay, so now this produces a bunch of zeros and ones as predicted by our now finely tuned logistic regression model. So this means that what we've done is perform some sort of gradient flow, for example, choose optimal parameters beta, so that we now have this function f of x dot beta, which is going to be our classifier. And if it's above 0.5, then yes, we predicted that person bought the product. It's below 0.5, and we predict no. All right. And so now we can, of course, evaluate. And so we end up with this somewhat odd confusion matrix, which just basically decided to predict that, let's just say that the 0 column, the first column corresponds to 0. They did not purchase it. So the way our predictor worked is it just says, we're going to predict everyone didn't buy the product. And they did this in part because we saw that there's 65 people who did and 35 who didn't, but also the geometry was such that when we try to use this model, it wasn't very good. So this means that we only have, assuming we've got a 100 points, we've only got a 65% accuracy. It's 100 points in our testing data set. So just to spell that out, use this accuracy score. And that just basically tells us what we can read off from the confusion matrix. Accuracy is 0.65. That's not great, especially when there was such a clean separation of, people who bought it and people who didn't. So this allows us to then revisit. Maybe we could pre-process this data. And so I have already alluded to this in earlier lectures, but there's good principled reasons for thinking that our first attempts were going to be frustrated. This has to deal with the fact that we're dealing with two units, age and salary. I guess salary was on the y-axis, age was on the x-axis. That have very different units. People are paid on the order of tens of thousands. Even in one of the poorest was like 19,000, 20,000, all the way up to 150,000. But still, that's 19,000. Compare that with an age like 19. You're on very, very different orders of magnitude, which means when you take dot product, the thing that's weighted by thousands is going to have a much, much larger impact in your logistic classification. And so this suggests that, well, it's just sort of arbitrary feature of our society that salaries are now on the tens of thousands scale and, years are on the tens scale. And so let's use something from scikit-learn called standard scalar and see what happens. So let's go ahead and, so now what I do is I create an instance of my standard scalar class, call it SCX. And this is an object, and I could update its parameters by applying this fit transform. And this allows me to produce both an X train rescaled and an X test rescaled. And so when I just look at the X train rescaled, you can see now that what used to be age and salary now are numbers basically between -2 and 2, or at least nearly. And that's essentially what's happening is they're mean centering each of these coordinates and then normalizing by the standard deviation, which again, one of the key steps you use in using or proving the central limit theorem. All right, so then let's look at what happens when we plot this now scaled data. Now the remarkable thing is that visually the data looks the same, which tells you that in some sense these are almost like what I'll use the word topological features. they don't care about sort of the bending and scaling and shifting. That wasn't important. You know, the fact that this was over and scaled in such a way, what really matters is the arrangement. It appears that there's a connected component of all the people who didn't buy, and then there's this other connected component with these weird flares that did buy. And it now looks like it's all centered around in the y-axis, 0.5 with deviation about 2 on each side, and then middle around, again, 0.5 with deviation around -2 to 2 on the x-axis. But the purposes of how we would classify just using our eyes, we would get the same answer. But let's see how this affects our classifier. Just cognizant of the fact that when we were using logistic classification, we were using a dot product, and that dot product was very sensitive to skewing or scaling one coordinate. And so if we run this analysis one more time, we'll use the same random state, so nothing changed. And we get the same pink box warning. Let's now make our predictions. All right, very good. And let's evaluate our new results. So let's just look at this confusion matrix one more time. Wow. Okay, and just because I'm lazy and I don't want to do addition, 87% is our new accuracy. And you could already tell that, yeah, we only had 13 misses. So I guess I could have done this in my head. 13 misses, so 7 false positives and false negatives. And that was all which essentially went to our inaccuracy before. And now we've only got 13 misclassifications instead of 35 full ones. So our accuracy is 0.87. And so I just want to offer this reflection. So just by pre-processing our data, we increased our accuracy by 21%. Imagine you were newly hired data scientists at some firm and they were trying to, increase their accuracy in predicting something. Maybe it's polling. You want to see if someone's going to vote for Trump or not. Or maybe, again, this is, thinking more realistically in terms of people are hiring data scientists to help with marketing tasks. What if you were able to increase the amount to which you're able to predict whether or not someone would buy a product by 21%? That might represent millions of dollars of new revenue for your company. And so just doing something as simple as rescaling can actually be very, very important. All right, so that's all for today. And I look forward to seeing you in class soon.